All right, so this is 5.15253. We're kind of hitting these really quickly, and this is a major part of calculus. Arguably, this is the linchpin. This is the part that ties everything together, okay? And if you remember, we said that all of calculus is about essentially two big ideas. One is the slope, and the other one is the area under the curve, okay? And area, slope and area. So today we talk about area. We have been talking about slope and derivative, and we even spent a little bit of time last week and a half talking about the antiderivative, okay? Well, today we're talking about area, specifically the area under the curve, and the integral. So it turns out, in lots of different situations, that it is very useful to know the area under f of x and above the x-axis in between 2 points. So we'll say it's very useful to know big A for area under f of x above the x-axis and between B/W, A and B. That whole thing is the area. It's useful because it can help you find the area of sort of weird regions. If you have maybe like, think of something that's curved, like maybe a road, maybe something that's bound by like a water or a river or something like that, and you know the equation which matches that function, then you can find the area between these two things. And if you can find the area between the curve and the x-axis, then it's not too much of an extension to find the area between this curve and another curve. It's also helpful then if you want to take this region and maybe revolve it around the x-axis, sort of like think of like a potter's wheel, something like spinning like that, or maybe something spinning around the y-axis. If you take that area and revolve it around, then you can think that might correspond to volume. And it does. Then that's just sort of like some very obvious geometric applications. If you've studied physics, you know that the area under the curve of various formulas give you different quantities, such as the area under the force versus time graph is going to give you the impulse. The area under the velocity graph is going to give you displacement, stuff like that. So, and there's a whole lot more than that. So anyway, this has lots of applications. So there are several methods to approximate that area under the curve. So these are the methods to approximate area under f of x. So I'm going to draw 6 xy axes because there are 6 methods that we're going to talk about. And then I'm going to try to make this like a curve, I guess, like some sort of. We'll try to do the same sinusoidal type shape. And we're interested in the region from A to B. try to make it kind of obvious that we're talking about a region. You know, this is trying to make it as generic as possible, but still kind of be kind of concise here. So at least there's a part where it decreases and then a part where the function increases. So if you're going to find the area under the curve, you could just slap a rectangle on top of there, but that's not very accurate. Your best bet is to divide it up into several different rectangles. Okay? Obviously, the smaller the better. So the question is, how are you going to draw your rectangles? And that's where we get these different methods. The first method, which I'll show you, is the left endpoint method, which says, all right, we're gonna divide this up into, I don't know, maybe divide it up into 4 rectangles, and this rectangle is going to go as high as when the left endpoint hits the function. And then I go across like that. So the left endpoint hits the function, and then go across like that. And then looking at these two, looking where the left endpoint hits the function, and then go across like that. I'll try to make sure that point right there, this point right here, this point right there between those two, and this point right there between those two. And then you've got the right endpoint. So I'll try to divide this 1, 2, 3. So if you follow along with me just for a second, if you look at here, I've got my left finger and my right finger here, my thumb. I'm going to go up until my right finger hits the function, and then go across. And then, once again, I've got these choices right here. I'm going to go up until my right finger hits, and then go across. Looking at this region right here, I'm going to go up until my right finger hits it and goes across. And then right here, I'll go up until my right finger hits it and goes across. And I would find the area of this rectangle plus this rectangle plus this rectangle plus this rectangle, find all 4 of those areas, and then add them up, and that would serve as an approximation for the nice, you know, the area under the red, but above the x-axis. But as you can see, there's some problems with these approximations. Ivan, what's the problem with those approximations?
They either overshoot or undershoot.
Yeah, they either overshoot or undershoot a little bit, okay? It's going to be a little bit of an overestimate or an underestimate. Now, if the function was completely increasing or completely decreasing, then it would be all under or all over. These aren't too bad in this particular case because I see I've got a little bit of area that's a little bit over estimate here, but I also got a little bit underestimate in there. That's kind of because of the way the function is, but there's no real guarantee. So somebody thought, hey, you know, I've got an idea. Rather than going all left point or all right endpoint, let's go to the midpoint. And so that's another method that is a little bit more accurate. So rather than going to the left or the right, I'm going to go straight to the middle in between those two. Kick left, kick right. Look at this right here. In between these 2 points, I'm going to go straight up to the middle. And this one right here is really pretty good. You can kind of see why the midpoint is a good approximation of that area, because you've got a little bit of an underestimate here, but you've got a little bit of an overestimate here. And that's kind of the idea for the midpoint method, or for creating midpoint rectangles. Any questions so far? All right. Well, keeping with that thought process, someone thought of this idea. What if we have all inscribed rectangles? That is, we don't lock ourselves in to a left endpoint or a right endpoint every single time. We look at both of them and see where they go up, and we pick the lower of those two endpoints such that our rectangle is guaranteed to be less than the actual area. So I'll divide this up into 3 sections. So if I'm looking here between left endpoint and right endpoint, and I want to have an underestimate, which endpoint would I choose for this rectangle, Rigel? Left endpoint or right endpoint? And the left is going to kick me all the way up here, and then as I draw this across, it's going to cause me. Okay, yes, it's going to be the right, because I put the dot right there. You see what I'm saying? And then I go, it's going to look like that. James, for this second rectangle right here, am I going to go to the left endpoint or the right endpoint based on my picture right now?
Right.
I'm going to go to the right endpoint, you're correct, because that's going to guarantee that I'm below. Ivan, what about for this rectangle that I'm looking at here, the way that I've drawn it? Left. Because the left one is going to hit right there, and I'm going to go across. And then again, it's going to be, and you know, your picture and where you draw your points down here might be slightly different than mine, so base your inscribed rectangles based on what's best for your picture rather than necessarily trying to match it to mine. Gracie, why do you think having an inscribed, going to inscribed might be a good idea to approximate the area under that curve?
Well, it shrinks your, not room for error, but like it gives you a boundary, because on the other ones, it could be, you don't know how much more or less it could be, whereas this one, you know it can only be more.
Oh, yep, I love it. It's gonna give you a lower boundary, and you say like, I know the area is at least this much. Yeah. It's probably a little bit more, but as she mentioned earlier on these other ones, you've got like a plus or minus value. Okay, so yeah, if you combine the inscribed with the circumscribed method, in which the circumscribed method is when you're choosing between the left endpoint and right endpoint, you always choose whichever one of those two is going to be greater. Then you can bracket the value for the area. You know that it's going to be higher than the inscribed and lower than the circumscribed. So the circumscribed, you go and you look at these two and you say which one of those two values is going to give me a higher value. So you pick your endpoint based on which of those is going to give you a rectangle, larger rectangle. Okay, and those are all good methods, especially those two kind of used together. And then somebody came along and said, hey, you know, why are we even using rectangles, right? Let's use trapezoids that are stuck on their side, okay? Normally when we think of trapezoids, our mind goes to, you know, that thing, right? Does anybody remember what the formal definition of a trapezoid is?
It's quadrilateral that has two parallel lines.
One set of parallel.
One set of parallel lines.
So those other two lines don't have to be.
Yeah, so the other ones don't have to be parallel. So we could put this vertically, and it kind of looks like that. Or make this guy have right angles and draw that, because this is a trapezoid, and that's also a trapezoid. And so what you do is between your two endpoints, you approximate the curve with a straight line. Now, it's not always going to be a straight line, and certainly very rarely is a straight line between 2 points, but if you're looking at you know, kind of in a shortest distance here, then yeah, it kind of is a little bit linear in between those. So I put a dot here on the left end point, I put a dot here on the right end point, and then just connect them with a straight line. This is the trapezoid method for approximating the area under the curve and above the x-axis between 2 points A and B. And if we had enough time, I would make you do every single one of these by hand, lots of practice, but I mean, really, we don't need to do that. What do y'all notice about that trapezoid method there?
It's really close.
Yeah, it's pretty accurate. Okay. Now, some things that you could do is you could also have like rectangles or even trapezoids for that matter with variable widths. Like this, you know, this one actually kind of is variable width. It wasn't intentional, but it kind of worked out that way, right? The really narrow region here, and then like kind of a larger region there, and kind of a narrow region there. Meanwhile, some of these other ones, it's a little bit obvious that the width here is more uniform. What we're going to be trying to do is try to turn this into something that we're actually not having to do the geometry, but we're trying to turn this type of thing into a formula. And anytime you're trying to do something into a formula, it's a lot better if everything's uniform and more regular, okay? But there was a guy who came up with a special name for you know, adding up those areas, okay? And that term is called a Riemann sum. It's the summation of like those areas under the curve. And the idea is that your area approximation is equal to the summation of those of each of those areas in the curve. So here's kind of like the procedure for approximating the area under the curve. So step one, you'd be given f of x. You'd be given A, you would be given B. Normally, someone would tell you, I want you to have this many regions that I want you to break it down into. So n regions or rectangles, if you want to think about that. I could also say slash trapezoids, but I'm not going to bother. So you're given all that stuff, and then you get to choose your method for approximating, or for splitting up, whether you want to choose left endpoint or right endpoint or midpoint rectangles or inscribed or circumscribed or trapezoids, okay? Then you would divide your region into n rectangles. Then for each rectangle, kind of channeling my computer programming here, so for each one of those rectangles, you would find the height. So after you found the height of each one of those, then you would use that height and multiply it by the width, or multiply it by the base, whichever way you want to call it, to find the area of each shape. just say each rectangle. And then you would add those areas up, or add them together. And that would give you your area approximation. So I want to kind of show you what that looks like very generically. Okay? So once again, we'll draw this one a little bit larger here. Here's our f of x. Here's a, here's b. I don't really care how many. We're going to split this one up into a few more regions. And I mean, if we want, I might just. So you could call this x value right here x1. You would call this one x0, I guess. And then you can call this one x2. Well, you know what? We won't have an x0. We'll have call this guy here. A can be x1, x2, x3, x4, and we can kind of go on down the list there. And the distance between those two, between any one of them, is delta x. The height, we would have to plug in, you know, if we wanted to find this, if we were using this endpoint here, we would plug in x2 into our function value, and that height would be like f of x2. If I wanted to find the height of this coordinate right here, I would plug in x3 into the function, and this value right here would be f of x3. This height right here would be f of x4, f of x5, and so on and so forth. So we kind of have some terminology. So if n is equal to the number of rectangles,
Thank you.
then your width, delta x, is going to like how many. The question is, how wide is each rectangle? Okay. Well, how big is your entire area, or how long is this segment right here? Let's say this is 100 units from A to B. It's 100 units from A to B, and I'm slicing it up into 10 rectangles. Then how wide is each rectangle going to be? 10 units, right? So the way you figure out your width is you say, what's the distance between A and B? So that's B minus A. And then how many rectangles are you going to divide that into? So you divide by n. So this is your width, your delta x right there, the width of your rectangle. So if that's the case, then the area of one rectangle, maybe we could say like this guy right here, would be f of x of 1 times delta x. Just the height times the width. The area of rectangle 2 would be like f of x2 times delta x. How high x2 goes. And like I said, This would all depend on whether you choose the left endpoint or the right endpoint, all that stuff. But you get the idea. And so then you would add all those up. So the area total, we'll say A sub t, would be A1 plus A2 plus A3 all the way up to A sub n at the very end. So mathematically, you know, anytime we, as mathematicians, have a way of writing a whole bunch of things into a shorter way, we kind of take it. So we say that the area total, let's put A total, equals, y'all remember the way that you write an indication for?
So,
Summation.
sigma.
Yeah, summation, which is the sigma. And I'll say I equals 1 to n of f of x sub I times delta x. That kind of seems to make sense. It's the summation of all of the height times the width. You good on that, Rigel?
Mm-hmm.
Okay. Now, we have just enough time for me to tell you some really cool stuff. And I'll show this to you by asking you a question. How could you get a more accurate answer?
By making n equal to infinity or approaching infinity.
By making n approach infinity. You said use a calculator.
Yeah.
But that's also accurate. You're both right. But
Making what
systematically,
you said is?
I would say this. I would say have more rectangles.
Yeah, you make the width smaller.
And you would end up making the width smaller. Absolutely. Those two things kind of go hand in hand. Okay? So, I could do this, like I said a second ago, for like 10 rectangles. But imagine if I made it for like 100 rectangles. I divided this up into 100 rectangles. Or 1,000. Or, what might even be kind of more interesting, what if I did it for 10, okay? And I recorded that number. Then I did it for 100, okay? And I saw what that new number was and how it related to the 10. Then I split up into 1,000 rectangles, and I found that area, and I looked to see, I looked to see what the trend was. What was it approaching? Does that make sense? Or if I did it for 1,000,000 triangles. So it's not just, not triangles, rectangles. So it's not just a matter of doing this for more rectangles, but it's executing this entire process for an increasing number of rectangles and to see where the trend goes. Okay? And as Ivan said, that's the limit process, the apply limit process here. So really, this is still like an approximation. The actual area is going to be whatever the limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I times delta x. Unfortunately, we're out of time, but that's okay because we'll show you next week that this is related to another idea which we've already seen. And it is fundamental to the theory of calculus. All right? So take notes on 5.1, 5.2, 5.3, and I will see you.
Just a reminder that we are going to fifth period now, and at 9:45 we will go to third. We're going to fourth period now,
She said fourth is like
and then third, okay?
Fourth period. So, Rigel, James, you guys can stay here if you want. Electronic stuff. Everybody say bye, Harley.
Bye, Harley.
Harley.